Okay, again, 2D motion with non-constant acceleration. It's similar to what we did with constant acceleration in that pretty much the same formulas and methodology apply. So, it is always true that the acceleration vector is the derivative of the velocity vector with respect to time, and that the velocity vector is the derivative of the position vector with respect to time. So if we know the acceleration vector directly as a function of time and can see that it depends on time, that it's not constant in time, then you just know you'd have to integrate to get the velocity and integrate again to get the position. So we'd have our integral of a dt, and it would give us our change in velocity vector. We'd have a velocity final minus a velocity initial. You'd have to rearrange that. To get the velocity final, you'd use that over here. You'd be taking the integral of the result of what you just did, a dt plus vi, and in this case it would be integral of our dr, which would give delta r. Now this looks like a double integral equation, but you can do them completely separately, so it's not like second semester calculus level stuff. This would give us our r final minus r initial, and you can rearrange that to figure out what the position at any future time would be. And that would look like integral over integral a dt plus vi plus ri. Oops, I forgot a dt in here. Let me add it in. I'm missing a dt in each of these steps at the following locations. Okay. Now it does get a little bit more complicated because you'll always have an x and a y component, but you can again separate it out and just handle the x and the y separately. So you could think about ax is dvx dt, and vx is dx dt, and then paired with that you'd have your ay dvy dt, and vy is dy dt. So you could just separate it out. It isn't that hard to deal with. We'll have at least one example, I believe, in the practice problems for the class, so you'll get an example of how this works. Vice versa, if you have a position and it depends on a time that is a power other than 2 or 1, or none. So if you've got t to the third power appearing in your position vector, or t to the second power appearing in your velocity vector, then you have a non-constant acceleration and you'd have to deal with that. And again, if you have some funny function of time, like an exponential in terms of time, or a sine or cosine in terms of time, then of course the acceleration is not constant and you'll have to use derivatives or integrals depending on which way you're trying to move things around. If you've got position and you want velocity and acceleration, take the derivative once and twice respectively. If you have the acceleration, you'll have to integrate once to get velocity and a second time to get the position. If you're given the velocity and it shows that there is a non-constant acceleration, you'll have to take the derivative to find the acceleration and the integral to find the position. So it's still as straightforward as it was. The real trick is just to identify when you have a non-constant acceleration. And again, if a depends on t at all, then non-constant acceleration. If v depends on t squared or higher, or some funky function, then you're going to get a non-constant a, non-constant acceleration. And if your position depends on t cubed or higher, or some odd function of t, then non-constant acceleration. So you just have to learn to look for those cases. They're relatively uncommon, but they do exist. All right, I think that's it for this section. Like I say, we should have some examples running during class. So look forward to those.